Hello again to all my friends. This is our first video in our Systems in Action units. It's going to be a little bit of an introduction to our forces. Now, I apologize for the way I sound. I'm feeling a bit under the weather, so this video is going to be really short but sweet. As always, it is Mr. Benjamin. Happy to be here. My colleagues, Ms. Podlipsky and Ms. Terrio, aren't with me right now. I'm actually recording this at home, but they will probably be in the next video and the videos after that as well. So we're happy. The learning goals for this video and this lesson is to describe forces. We're going to hear that word a lot. Forces, which are also known as pushes or pulls, and their effect on an object, because forces always act on an object. We're also going to discuss the impact that gravity has on mass and forces. Gravity is probably the most common force we encounter every day. We'll talk about that a bit later. So, force. What is a force? We're not talking about Star Wars. By the way, I saw the new Star Wars, which isn't really new anymore. I'm just really late on this. It's called The Force Awakens. I actually didn't like it, but that's another topic for another time. Anyways, a force is any push or pull. And that's acting upon an object. So like I said before, the most common of this is gravity. Gravity is all around us. Gravity is what keeps us in place. It's what's keeping me sitting on my bed as I record this video. It's keeping my iPad on my bed as well. It is keeping my bed in my house, which is on planet Earth. If we didn't have gravity, we'd all just be floating around. It would be really, really fun, but it'd be very hard to get some work done. Aside from gravity, we have other forces as well. Another very common force is friction. And friction is the resistance of an object from moving. So if we consider things like, say, ice. Ice, for example, has very, very low friction, so things kind of slip and move on ice. If you've ever been on ice and you haven't been wearing skates and you don't really have a great sense of balance, you're probably going to slip straight over. The same goes with a banana peel, but I've heard that banana peels don't actually do that. People might have done research into that. There's probably a Mythbusters video. It's kind of a shameless plug, I'm sorry, but there's probably a video on that somewhere on the internet, so you can find that. But friction tends to hold things in place. So if we think about if you're ever walking on sand or dirt or anything like that, you feel kind of coarse, and it's much harder to slip on that than it would be on ice or water, which has very little friction. Now we can also classify forces in different ways. Forces can either be contact forces or they can be forces at a distance. A contact force would be just as it sounds, literal contact. So if a friend of yours gives you a little tap on the shoulder or maybe a punch in the face if you're not being very friendly, or my pen, my stylus, touching this iPad right now, that is a contact force. I am putting pressure on the pen towards the iPad, which is leading to pressure on the iPad. These kind of look like snowflakes, they're cute. But the other types of force we have, they're not contact force, they're at a distance. So contact slash at a distance. Now these forces act upon us and we don't even really know it. So gravity is an at a distance force. Oh, that looks horrible. I'm going to get rid of that and write it again. Gravity, sorry about that, is an at a distance force. We don't really see it acting upon us, but we know it's there. We can feel it. If you've ever tried to lift something that's heavy, that's gravity acting upon it. In fact, that's how the whole concept of weightlifting works. You're taking heavy objects and lifting them up, and your muscles tend to resist it, and you feel pain, and they grow from that. So before we move on to masses and weights, we're going to talk about how forces are measured. Forces are generally measured in newtons. The reason for that is Sir Isaac Newton was the one who discovered the force of gravity, where he had the tree. I'm going to draw a quick tree here. That looks terrible. But anyways, the apple fell on his head. I can neither confirm nor deny this story because I wasn't there at the time, but that's what we're going to go with. That's why we call forces newtons, or that's why we measure them in newtons. Now, the way we measure the amount of force that an object has, or the amount of newtons that is within the object, is by using a special device known as a spring scale. So it is literally an object here with a spring inside of it that continues all the way, and there's also a scale written on the edges. And as the object weighs down the spring, you get a different reading. So this gets pulled down depending on how much force the object has. So if an object has a very small amount of force, it's going to be a lower reading. If an object has a very high amount of force, it's going to be a higher reading. So a lot of the times when we talk about forces, we need to talk about an object's mass, and we always want to clarify what the difference between mass and weight is. We tend to ask each other, how much do you weigh, which is an incorrect question because we really want to know how much mass does your body contain. So mass is literally the amount that is in an object. So if I had a cube here and we were measuring the volume, that would be the total amount on the inside. That's the mass. That number is not going to change for any reason except for if we were to take a chunk out of it. Then the mass would change. Our weight changes for that same reason because we are either losing weight or gaining weight. However, our weight would also change if we were on different planets. So we have Earth right here. I should probably get some green in there. So this is Earth. We've got your land masses. I know this looks really, really bad, but bear with me. And the rest of it's kind of water. And Earth has a specific amount of gravitational pull. That's what gives us our weight reading. Weight is based off of gravity. If you go to a different planet, a planet that's smaller, for example, Mars. This is Mars. It might not look like it, but it is, trust me. And this is Earth. Your weight will significantly reduce on Mars. You weigh less on Mars. I hope everyone can see that. The reason for that is the gravitational pull on Mars is much, much less than it would be on Earth. So that's something we need to keep in mind when considering masses and weights. The way we calculate the force of gravity and the amount of mass, or the newtons that we contain, is by taking this formula right here, by using this formula. So Fg, which is the force of gravity, is equal to m times g, or mg, where m is the mass of the object, and g is the Earth's gravitational pull, which is a constant, which means that number is never going to change. It's 9.8 newtons per kilogram. So what we're going to do, keep this in mind, keep this formula in mind. We're going to try this, we're going to try to find our own force of gravity. So for example, we always start with our formula when we have a formula. And I'm going to make some space for myself here. In fact, I'm going to do it a different way. Bear with me for a second. Alrighty, I'm not sure how that looked on the video, but we're going to go with it. So, we know that Fg is equal to m dot g, where m is the object's mass and g is our constant, which is gravity. G equals 9.8 newtons per kilogram. So, I'm going to use my own mass. Last time I weighed myself in kilograms at least, which is the unit we need to use, I was around 70 kilograms. So, my Fg, or my force of gravity, would be equal to 70 kilograms times 9.8 newtons per kilogram. So when we multiply this out, the kilograms cancel, and the number of this value, it's around 600 and something. Just grab my calculator real quick. So my force of gravity is 686 newtons. Pretty heavy. So now I'm going to ask you to find your own force of gravity. But don't post it, don't tell me it, I really don't want to know. I just want you to write out that formula, Fg equals m times g, and understand that m is the object's mass and g is the gravitational pull, which is a constant. G equals 9.8 newtons per kilogram. As always, we say thank you, or I will say thank you at least, and put a big smiley face. Have a great day.